In this video I'm going to explain how we can find antiderivatives of expressions that involve inverse trig functions. And notice that we're not saying the antiderivatives of inverse trig functions, because really we're finding integrals of expressions which lead to the inverse trig functions. And so if we look at the ones that are on our formula sheet there, you'll see that they're basically just the derivatives of inverse trig functions kind of flipped around in reverse. And so we're saying if we take the antiderivative of something of this form, then we know that it's going to be an inverse sine function, plus the constant of integration there, because the derivative of this is an expression of this form. And same for inverse cos and for inverse tan. So that's the way they appear on the formula sheet. And then of course we can add our domains, and we know those from considering the derivatives, and also because these here are undefined for any values of x outside those particular domains there. So let's get straight into trying some questions that actually use these results. So we'll grab a couple of ones that look a little bit different and make sure that we can work with those. So some of them are going to look pretty straightforward, and we can see straight away how they relate to those particular results. So if I had something like this, the integral of 1 over the square root of 9 take x squared with respect to x, then we can look at that and say, well, that's very much of this form here, and in fact even that number there is a square number, so I can fairly easily write that precisely in that form by just writing that as a 3 squared instead of 9. And then I can see that my value of a is 3. So the integral of that is going to be the inverse sine of x over 3. And just remember, because it's an indefinite integral, we need our constant of integration there as well. But things aren't always quite as straightforward as that. So even something like this one here, if I had the integral of, let's say, 1 over 5 plus x squared dx, well, the first thing we should notice there is there's no square root involved, and there's a sum there on the denominator of a number plus x squared. So we're definitely looking at one of these ones here rather than either of those. So it's going to be an inverse tan one, but we need to do a little bit of work to get it in the form where it's a over a squared plus x squared. So we can start off by seeing that that value there, the 5, has to be our x squared. So I'm going to change this into a 1 over, let's make that root 5 squared plus x squared dx. So if that's a squared, I need the numerator to be a. So what I'll do is basically sort of force it into that form and write that as root 5 on the numerator. But then I need to recognize that 1 is equal to root 5 times 1 over root 5. So I'm going to put a 1 over root 5 there, such that the product of this and this is equal to 1 there. So now this is in the form a over a squared plus x squared, this here, so I can integrate it into that. And so I'm just going to have the 1 over root 5 out the front times inverse tan of x over a, which is root 5 plus 6. So I could leave it in that form there, or I could rationalize the denominator, which would make it inverse tan of root 5 over 5x plus c. So sometimes a little bit more work involved to get it into the form that we can use one of those results.